Okay, so last time, which was Thursday, we talked about directional derivatives. Okay, so we already know that you have like the derivative, there's the partial with respect to x and the partial with respect to y. That's a secant line where your other point is formed by. So you start with a point, you move away in the direction of the x-axis, make a secant line. That will give you the partial of f with respect to x. Start at your point, move away along with the y-axis. That forms your secant line. That will give you the partial with respect to y. So we started wondering, like, well, shit, what if you want just like the derivative in some random ass direction? So we came up in a direction of the variable of the vector u. So we came up with that. So remember, there was this point. You get your other point by rotating some distance away from the parallel to the x-axis, and then you move in that direction. So u is some vector which points in the direction you want. The angle theta tells you in what direction you're pointing in respect to the positive x-axis, and then you get this formula: the directional derivative of f at a comma b in the direction of u is the limit as h goes to 0 of f of a plus h cosine theta plus b plus comma b plus h sine theta minus f of a comma b all over h. Okay, and I remember last time we did this example where we wanted to calculate the directional derivative in this direction u, where the angle theta was like cosine inverse of 3/5. Okay, we drew the picture, we set up the thing, and then I remember what happened was I got stuck in some calculation. I was like off by one number and it wouldn't simplify. I actually never found, like, I went and I looked, I couldn't figure out where I made the arithmetic error. So what would have happened is it would have simplified and we could have plugged everything in. This is a really annoying way to find directional derivatives, so I want to give you a better, easier way that's nicer to use than the limit definition. So how can we find the directional derivative without the limit definition? Okay, so luckily there is a way to do it. Definition. So let me show you how. Okay, so if you want if you want the derivative, the directional derivative. Stop. Shh. If you want the directional derivative in the direction of u, Burrito doesn't want you to find this out. If you want the directional derivative in the direction of u of this function f of x comma y, the easy way to find this is find the partial with respect to x at x comma y, multiply that by cosine theta, plus the partial of f with respect to y at the point x comma y, and multiply it by the sine of theta. And this works if you have, oh my god, Burrito. If you have some direction, so if you have some function f of x comma y, you have independent variables x and y. You need those partials to exist. And then you want it in the direction of u, where u is some vector that has components cosine theta, sine theta. Burrito, please stop. Ugh, someone's like moving around outside. He's just like so pissed off at them. He's throwing me off. Does that happen to anyone? How is everyone's... I'm going to pause for a moment because I've been distracted by him. Do we struggle with this at home too? Like distraction from noise and such? My dog with the mailman. Yes! Yes! Oh my god. When the mailman comes by, he is so angry. And like, I know it sounds really bad, but like, lately, my patience with it has worn so thin. Oh, I need to spot for myself. My patience with it has worn so thin. Like, I'm just like, I just sort of feel like saying, you burrito, like, I'm tired of this. I mean, I get it, he's a dog, and he, like, has, like, basically no control over it, but damn, pisses me off. And then, like, my train of thought gets, like, completely yanked, and it's, like, already hard enough as it is to sort of do this, which is, like, one of the reasons I would like to go back. You know, it's, like, that's the whole point of having a college, right? Like, there's a quiet place. There's, like, no one else there bothering you. I mean, unless you have friends or something, but... You know, I definitely feel for everyone who says they would like to go back. I was walking yesterday and a chihuahua came at my dog. I tried to bite the hell. Oh my god, that is the worst when they're, like, you deal with bad dog owners. Like, they just sort of let their dog, like, do whatever the hell they want. They aren't even like, oh man, I'm sorry, like, my dog just sort of sucks. You know, and they just sort of sit there like, oh, suck it, like, I don't care. Yeah, no, I know what it's like, you know, I've definitely dealt with people where I'm like, are you gonna, like, do something with your dog, or just, like, everyone has to, like, eat your shit. Like, it's super upsetting sometimes. That's why I always wear my headphones, because even though, like, none of you really, even though you guys rarely talk, it just sort of buffers the sound. Like, when my kids get up to have breakfast or, like, eat lunch or something and I'm lecturing, like, definitely sometimes it's, like, too much. Burrito, stop! I need, like, a muzzle for him. They acted as they were sorry. Oh my god. Yeah, no, dealing with people like that, it's such a pain. Okay. So, let's do an example of this. So, example. We are going to let theta. I wonder if I could do. So we're gonna let theta be equal to the arc cosine of 3/5. And we are going to find the directional derivative of f of x comma y equal to x. Let's put that on the new line. Equal to x squared minus xy plus 3y squared. And we also want to know, well, what's the directional derivative in this direction u of minus 1 comma 2? Okay, so according to our formula, the directional derivative, the derivative in the direction of u for f of x comma y is equal to the partial of f with respect to x times the cosine of theta plus the partial of f at x comma y times the sine of theta. So we already know that our theta equals cosine inverse of 3/5. Okay, so this makes life easy for us. We're going to take the partial of f with respect to x. So that's going to be 2x minus y. And then we made a multiply by the cosine of theta. We had calculated that last time. If theta is the cosine inverse of 3/5, if you take the cosine of that, it just cancels and you get 3/5. Okay, then you need to do the same thing for f with respect to y. So if you take the derivative with respect to y, you're going to get minus x plus 6y. Now, if cosine of theta equals 3/5, we can just solve this. Just imagine drawing a right triangle with your theta right here. Cosine is 3/5. Cosine is adjacent over hypotenuse. Burrito. Oh my god, you're killing me, dude. There's your y. So you get 3 squared plus y squared equals 5 squared, which will be 9 plus y squared equals 25. So your y squared will be equal to 16, so your y is 4. So what's your sine of theta? 4/5. Okay. So now you can go and multiply this through. Let's put this one over 5. So you're going to get 6x minus 3y plus minus 4x plus 24y all over 5. Cool, so that will be all over 5. 6x minus 4x is 2x. Negative 3y plus 24y is plus 21y. Okay, that is your directional derivative. That's what we were supposed to get yesterday. We did not. We were like really close though. If you scroll up, we were probably getting really close to that, but something happened. It was sad. But anyways, you can see that this is a lot easier to deal with. Okay, so here's your directional derivative, and then what is your directional derivative at 1, 2? Fairly easy to figure out. So what's the directional derivative at negative 1, 2? Well, you get 2 times negative 1 plus 21 times 2 over 5, which is 42 minus 2, which is 40 over 5, which is 8. Okay, so I'm going to pause and see if there are any questions about what I plugged in and what I got. And then we'll talk about the meaning behind it in a moment. Okay, hopefully it's pretty straightforward how I plugged in to the formula on the first step. And then I want to know, are there any questions about where any of this came from on the second step? So I'm just going to pause for a moment, let you think. While I stretch and drink my coffee, because it's sort of early. Okay, so there's 2 things here we wanted to find. This here is my formula for the directional derivative. And then what did I do? I evaluated the directional derivative at a particular point, negative 1, 2, and what did I get? 8. So let's talk about what that means, I guess. So you can imagine that we have our x and y plane. Here's our x and y plane. Here's the x-axis, here's the y-axis. The point that we're dealing with is negative 1. Holy shit. Stop. Negative 1, 2. Okay, now, that's my first point. I want the directional derivative where I move away according to, what was my angle? My angle was equal to the cosine inverse of 3/5. Okay, and if we draw that as a picture, I'm just going to redraw it, right? You have your angle theta right here. And what you get is a 3, a 4, and a 5. So what that means is, through this point right here, I can draw something parallel to the x-axis. And how am I going to rotate away? I want to rotate away so that I end up with a triangle. So I'm rotating away, that I'm ending up with a triangle such that adjacent to that angle is length 3, opposite that angle is length 4, and the hypotenuse of that angle is length 5. It is in that direction that I'm going to get my second point right over here. This point is -1 plus h cosine theta, comma, 2 plus h cosine theta. So it's with this blue point. Sorry, it's with this green point and this blue point that I'm going to be forming my secant line. So the directional derivative is saying, like, look, you have your point -1 comma 2. This other point, you move away in this direction theta and you get this green point, and then you're going to take the limit of those 2 points. So if I was to take the limit as h goes to 0 of f of -1 plus h cosine theta, comma, 2 plus h sine theta, this is supposed to be sine right here, minus f of -1 comma 2 all over h. If I take the limit of that secant line, my tangent line at the point ends up being 8. That's what that 8 means. So obviously you can get these tangent lines in different directions, right? And the formula we just went over is a much easier way of doing this limit calculation. Like, obviously, everyone I hope was pretty convinced yesterday that doing that limit calculation really sucked. Okay, so I'm honestly interested if you have questions. I know that maybe you don't. I woke up at 6 a.m. this morning, so like my brain is actually smoothly functioning, which is good. I'm actually happy about that. I know that it's easy to be a zombie in the morning, so I just want to give you time to think about this for a little bit, just in case there are questions. Have we all had enough coffee to think this morning? Or enough sleep, for that matter? Thank you for asking me to wait. I will wait. No, I like, Marshall, you always have so much honesty. I like it. Yeah, not enough sleep. It is super important. Does anyone know what several days of 30 minutes less sleep than what you normally get will do to your cognitive state? I know people are writing, so I'm just going to pause for a moment. Does anyone have any idea what a cognitive impairment level from just 3 to 5 days of 30 minutes of less sleep every day will do to you? Yeah, it's actually the same as drinking 1 or 2 beers. Seriously. If you don't get enough sleep, you might as well just fucking down a Foster's and show up to class. The big ones. Has anyone ever seen those gigantic Foster's cans? I mean, most of you probably aren't old enough to drink, but who knows? But yeah, it messes with you. Sleep is super important. You're not old enough. I think it's just probably me and 1 or 2 other people who are old enough to drink here. Alright, so I'm going to give you some more time. I can't emphasize it enough. Sleep is very important. I know that sometimes I definitely do not get enough sleep. I was actually getting enough sleep every day up until about 2 weeks ago. Did anyone else recently have like a change to their sleep schedule? Or was that just me like finally like giving in to like staying up late at night and saying fuck it, like YOLO? I'm like sort of curious. Just me? Oh, it's hilarious. Yeah, no, recently I just was like, oh shit, damn, man. 3 hours is not enough, dude. That's no bueno. That is no bueno. But yeah, like recently, I don't know what it was, but I just was like, you know what? I feel like staying up and wasting time. And so I'd find myself at like 2 in the morning. I'd be like, oh no, I'm going to regret this. More times than I care to admit. Sometimes even later. And then obviously I do this in the morning, so it didn't work out very well. And then it became just a spiral. And I was like, crap. Okay. So I'm going to scroll down now, and I want to talk a little bit about this formula that we just did. There is some interesting stuff with this formula. And there is a special significance to it. Okay, so what's the formula I'm talking about? I'm saying if you want the directional derivative, if you want the derivative in the direction of u for your function f, how that's the partial of f at xy times cosine theta plus the partial of y, partial of f with respect to y times the sine of theta, where u has those components cosine theta comma sine theta. Okay, so if you look at this, there's something. So remember how we talked about the dot product? If u has components a and b, and v has components c and d, what do you get when you do their dot product? I know it's like a while ago, but thinking back, if your u is a comma b, your v is c comma d, what do you get when you dot them? Do you remember? Do you remember? That makes me think of that one song. Dancing something something in November. I guess I'll answer for you. Yeah, in September, not November, my bad. Roger remembers the song at least. So if you dot product two things, you take their components and you multiply them. So you take the first components of u and v, and that's going to be a times c. And then you take the second components, b and d, you times them and you add them together. And if you look at this formula, what are these two things? They are the components of u. And they're being multiplied by these other two things, which are maybe the component of something, and they're being added. Okay, so there is something called the gradient of a function. And the way we symbolize the gradient is with this upside down triangle. It is called a nabla. This means take the gradient of the function f. The gradient of the function f is a vector. where the first component is the partial of f with respect to x, and the second component is the partial of f with respect to y. So that's it in component form. You could also write it in unit vector form. Oops. Partial of f with respect to x times unit vector I plus partial with respect to the partial of f with respect to y unit vector j. And what this means is, well, if you look, this right here has that as its first component, and this right here is the same thing as the second component of that. So what this shows you is that your directional derivative of f in the direction of u is just the gradient of f, which is this vector, dotted with the vector u. Because, like what I wrote, u is this vector up here, and the gradient of f, the gradient of f is this vector right here. And when you dot them, what do you get? You get the formula, because you take the partial of f with respect to x, multiply it by cosine theta, add together the partial of f with respect to y, and multiply it by the sine of theta, right? It's just the components of those two vectors multiplied and added together, which is the dot product. Okay, so what this does is it simplifies how we write the derivative, this directional derivative. Instead of thinking like, oh, it's the partial of f with respect to x times the cosine of theta plus the partial of f with respect to y times sine theta, really what's going on is that you're taking the gradient and dotting it with the direction vector. And if you notice, that's why you have the u right here and you have the f right here. Those are the two things that show up in the formula. So what this is telling you is that if you want the directional derivative of f in the direction of u, that is the same as taking the gradient and dotting it with the u vector, the direction vector. Okay, I'm going to pause and possibly say that again, because it's important to write that down. Actually, let's just type that shit. Oh crap, it's doing its weird thing. There we go. Okay, so the directional derivative is just dotting the gradient of f with the direction vector u. Or is just the dot product. Okay, so let's just do some examples of calculating the gradient. Or should I leave it here a moment? I don't know. Is it okay for me to move away from here? Can I move away or shall I stay? Stay, okay, cool. Well, actually, in that case, since we only have like 5 minutes left, I'm just going to leave this here for people to copy. If you are done copying, I think we're just going to finish here. We'll pick up tomorrow with the gradient. So, before you leave, make sure you check in. Awesome.